So thank you very much for the organization and the invitation. So this talk would be a bit of a different focus. I'm going to talk about nonlinear spectroscopy, but now used in the optical or near infrared. Okay, and these are the people that were involved. A postdoc who just left, a grad student, and then a brilliant undergrad student. Okay, so I'd like to sort of start out with something that is rather basic and I guess dear to the hearts of those who come from quantum optics, and that is the AC Stark effect. Okay, so it has played a major role in as a technological tool, not as a kind of interesting physics in cold atom physics. So basically, I'm sure all of you have seen optical lattices and how this is used to realize sort of many body systems, or more recently from Antoine Brevet and Michel Lukin and company, the optical tweezers. The basic physics there is the AC Stark effect. Okay, so the idea is that if you take a strong laser field and then detune it from an optical transition, you need, typically you are dealing with an anharmonic spectrum, then the ground state energy shifts by this amount, which is the Rabi coupling square divided by the detuning. Okay, so which provides, if you have an inhomogeneous laser field profile, it provides you with the an attractive potential. Okay, and what is really important here is that if you have one atom or n atoms, doesn't really matter. So the shift is independent of the number of atoms in this. So then one can ask what happens in a semiconductor, and we're not the first to ask this question. Actually, Nuh did beautiful experiments as well as Han Guang. And the answer is, well, if you detune your laser a lot, and in this case, the measure is the exciton binding energy. So if you're detuning from the conduction band is larger than the exciton binding energy, then it's more or less like a bunch of atoms, right? So it's not, you can say that you can excite electrons from different valence band states, and the gap is not exactly the same, but you will still get an AC Stark shift of this magnitude. And again, as Nuh showed a few years ago, if you detune more and increase the intensity, then you can also see the Bloch-Seekert shift, which is the anti-resonant. Now, the question that I'm interested in is what happens if the detuning is much larger than the line width, but is small compared to the exciton binding? And then how do we think about AC Stark shift? Because particularly if our excitons are tightly bound, they're to a good extent describable as harmonic oscillator modes for each center of mass momentum. And we know that if you derive a harmonic oscillator mode, all that happens is that we generate a coherent state amplitude. Okay, so what happens in the case of semiconductors, and this again is also not such a new thing. It was analyzed by Stefan Schmidt-Ring in late 80s, and then first experiments were done by Daniel Scherma in 90s. The effect is that you still see an AC Stark effect, but now the physics is rather different. It really arises due to the exciton-exciton interaction. So even though you are detuned, you generate a virtual excitation of virtual exciton density. And these excitons interact with each other. And these interactions are the reason why you have the anharmonicity in the spectrum. And this anharmonicity in turn results in the AC Stark shift. Now, the important point here is that the detuning dependence is 1 on detuning squared, whereas the two-state effect, single particle effect, depends on reciprocal with the detuning. Okay, and this dependence actually comes about because the exciton population, if you detune, is going to be given by the Rabi frequency square divided by the detuning square. So I can write this actually as the interaction between excitons and the exciton density. Okay. So this, as I said, was analyzed theoretically, And what is interesting, what we found interesting, is that because of the fact that the shift is proportional to the interaction strength, we can actually use this as a tool, first in rather straightforward monolayer semiconductors, then in moire systems, as a way to analyze and get extra information about the elementary optical excitations. And how they interact with each other will tell us information about their relation. And this is what I'm going to try to convince you that this is the case. So as usual, I will start out with elementary optical excitations and in monolayer transition method like chalcogenide. So this is where we do the experiments. Then I'll try to convince you that we can indeed use AC Stark shift to determine excitonic interactions. And there is one piece of interesting information there. And then I will apply this to the spectroscopy of a moire heterostructure molybdenum diselenide. All right. So as I said, the physical system we're interested in are TMDs and predominantly molybdenum diselenide. So this is a valley semiconductor, and the interesting physics takes place in the time reversal symmetric points, high symmetry points of the Brillouin zone, and there is polarization selection rules that sigma plus incident light only causes, say, excitations in K valley, and the opposite is true for minus K valley. And so you never almost see band-to-band excitations because of the reduced screening and relatively heavy mass. The electron binds to the hole it leaves behind in the valence band rather strongly with the binding energy of 230 milli-electron volts. And this corresponds to a Bohr radius of 1.1 nanometer. So it's important that this is, when you also study moire, that this is the smallest length scale in the system. So that has some advantages. And it's not always true. And again, I'll come back to that as well. So I should also say that if I had a suspended monolayer, this number is predicted to go up to 500. Okay, so as I said, the excitons are the elementary excitations. They carry a large oscillator strength.
The number is for on HBN or something?
That's encapsulated with HBN. Yeah, and actually these are very nice measurements by Scott Crooker done in the high magnetic lab. So it's really, the values are determined from the diamagnetic shift, which requires more than 50 Tesla fields in order to okay. So yeah, so what is also nice in the system is that the exciton lines are almost radiatively broken. So they can actually reflect incident light with up to 85%, that's the maximum number, reflectivity. So they're at a certain frequency, of course, only a single frequency, they reflect light almost as good as a lousy mirror, like an aluminum mirror. Okay. So, and this has to do with the very small Bohr radius, and one aspect of it for us, particularly if you try to use excitons to study electrons, which is the ultimate goal in this system, in these kind of experiments, at least for us, is that we can treat exciton as it interacts with electrons as a robust impurity. Okay, so it interacts, it senses the state of the electrons, but it doesn't change its own function. Okay. Now, the drawback is that the interactions are weaker because since the electron and hole are so tightly bound, they're basically they hardly see each other. And that's, you can actually show that the interaction strength scales as the Bohr radius. Okay. So now let's look at a monolayer. So when we can actually put top and bottom gates to control the doping, and when the monolayer is charge neutral, as you scan your laser frequency, or in this case, it's just white light, you see that it's dominated by one resonance, and that is the 1s exciton. If you go further up, you see the 2s, 3s, etc., the Rydberg series, but these are typically, at least for molybdenum biselenide, rather weak. Okay, and if you take a line cut, you see that you have reasonably sharp exciton line, which has a dispersive line shape, and that's due to optical interference effect due to from the light reflected or generated by the excitons and the light reflected at the dielectric. That can be eliminated, but it's not terribly important. Okay. So the interesting physics comes about when you dope the system with electrons. Then you see two things. There's a new resonance that appears on the right-hand side, and then the exciton resonance broadens and pushes. And this we actually explained a few years back together with Eugene. So the way one can think about it is that this interaction between exciton and electron, one can view it as a scattering problem. So my incoming scattering state would then consist of an exciton and an electron. And if these are in opposite values, then they interact with this 1 over r to the 4 interaction, and they support this interaction, or this potential supports a bound state, which is referred to as a trion, a free-body bound state. Now, the effect of this trion is that as these particles come close, they can hybridize with the trion. And because of this hybridization, their energy is pushed up, and that results in this blue shift, or an effectively positive interaction. And at the same time, the molecular state, upon dressing, it's some exciton character, and that gives its oscillator strength as well as direction. Okay. So that's then the explanation. So we, following up on the terminology from cold atom physics, we call this attractive polaron and the repulsive polaron. And what is important here for the latter part of the talk is that this attractive polaron oscillator strength, even though it's not totally clear from this curve, that it, at least for densities up to 10 to the 12, it increases linearly with the electron density in the opposite value. Okay, and this is an exact expression actually for the oscillator strength at low densities. It's the exciton oscillator strength times the square of the product of thermal momentum and the trion Boolean.
What's the origin of the 1 over r to the 4th? Is there a simple?
It's charge polarizable object interaction. That's it. That's it. Okay. So that's the story, and this interaction is only valid if the two are in opposite values. This is maybe not terribly important for the talk, but this is what the property we use to study magnetization. And this is an experiment at 14 Tesla. You see that one polarization shows very nice attractive polaron resonance, whereas the other one doesn't, because at these fields, the electrons are completely valley polarized. And say in this case, minus K valley, and then you only see the polaron formation in the plus K valley, or the sigma with sigma plus, and this is the line. Okay. So now that's our basic. So now I'd like to sort of describe the probe setup, which is rather simple, and particularly since instead of trying to make sort of terahertz lasers and worry about how to couple them to low temperature materials, we buy lasers and then just couple them through usual transparent windows. Okay, so the idea though, I mean, there's one complication that you start out with the type sapphire laser. You will be exciting with a relatively narrow bandwidth, 200 femtoseconds or so, pump pulse that whose detuning we want to change. At the same time, we want to probe what this pump does, and to be able to, for a range of natural frequencies, natural excitation frequencies. So to be able to do that, we need to broaden the probe, and this we do so by using a nonlinear fiber. Okay, so the probe is then substantially broader in frequency domain and also shorter in time domain than the pulse. Okay, and for most of the experiments, we'll assume that they will be closer. So this is now what happens if I go to charge neutrality. So I have my exciton resonance, and then I sort of changed the time delay between the probe and the pump pulse and plot how the exciton resonance responds as this probe is changed for a given detuning. I think in this case, the detuning is about 20 millielectron volts. So you see that it doesn't look too nice. Actually, it is nice. I mean, what is really important here is that basically -1 picosecond and +1 picosecond response to optical response is almost identical. And that was the goal, that we perturb the system, but we do this by this off-resonant laser such that we don't create dark excitons, we don't create heating. It's just that the perturbation is there only while the pump pulse is there. Okay. So the reason why it looks kind of dirty is something that is known in nonlinear optics. This is free induction decay. Whenever the probe comes before the pump, it actually interacts with the pump field that comes after and then results in these cycles. So it's a consequence of the fact that the exciton is really rather coherent, and you'll see that this is not always the case. Okay. And that, again, is the sort of the cross-section, how there is a blue shift, interactions are repulsed. Okay. So what we did first is to confirm that this shift is not your usual AC Stark shift. And to do that, we changed the pump detuning up to values that are actually approaching the exciton binding energy. And you see that the shifts are fit extremely well with the 1/d tuning square dependence, and 1/d tuning fails. So we're basically confirming what Stefan Rink calculated 35 years ago. Okay? So this is then the experiment where the pump field, whereas we changed the detuning. Now, the exciton density depends on the intensity, and the exciton shift increase depends linearly on it. That's also not so surprising. And this all basically tells us that the shift is indeed described in these terms. And maybe it's also a kind of a negative result from the slope. You determine what the exciton interaction strength is, and it's 0.1 microeV microscope. So that probably doesn't mean much to you, many of you, but just to say that it's about factor of 30 smaller than gallium arsenide, which is more than what theory would predict, right? According to sort of, if you just take the exchange-based interactions, it should be only smaller by a factor of 4. Again, that's, if you're doing polariton physics, that might be interesting, but it's not. So then we turned it to, we dope the system. We look at the response of the attractive photon. So to that end, we tune the laser, the pump laser, to the red side. If you tune to the blue, actually that's one prediction that the shift should always be blue, unlike the usual AC Stark effect. But here things get ugly, right? Because basically, when we talk about having electrons, we actually have a many-body system, and then we have a continuum of excitations. It wasn't me, was it?
Maybe disconnected, reconnected.
So let's do that.
Well, then I don't know what you do. But I didn't understand how to get him.
Well, let's see.
Who's writing?
Yeah, because I plugged, unplugged, it didn't help. There's a limited set of things I know how to do.
Well, while we're waiting.
Yeah.
Can I ask about these polarons? So what's being polarized? I'm used to thinking about a polaron as like a charge in the phonon.
It's really the electron, the Fermi sea is, if you want, polarized in the sense that you generate electron hole pair excitations, particle hole pair excitations across the Fermi sea. And these excitations then dress the exciton. Great. And
I did the same thing as
basically, so this dressing, I will have a picture for this rather cartoon, that what it happens is that you know, you have a Fermi sea, and because of the interactions between the two, if you are forming an attractive polaron, then you basically localize an electron around the exciton and create a Fermi sea hole then in the immediate neighborhood. And that actually plays an important role. So maybe it will be clear. So yeah, I told you that if the resonance is not very coherent, the spectra looks even nicer. So this is for the attractive photon, not so much of the free induction decay. And you see that there is sizable increase. The dependence is 1 over delta omega squared. The intensity dependence is linear, except for this last point. So things check that it really looks like we are predominantly exciting an attractive polaron at these detunings, and we're seeing the AC structure associated with it. So, so this doesn't work now. Okay. I can also not change it from here. So, all right.
I can miss slide. Sure.
Let's see if this will work now. Yeah, okay. So, yeah, so here what I show you is that just as I advertised, if I were to use transfer matrix fits to calculate the oscillator strength or the radiative decay rate of the attractive polaron, it actually increases linearly with the electron density. So what we're looking at here is the electron density. So this is basically a confirmation of what I told you before. And if you look at the line shift, that also scales linearly with the electron density. Okay, so at this point, you know, if you look at this, it might look a bit boring, but there is an important difference here. This linear shift does not go to 0. It crosses at a finite, if you continue, at a finite line shift, right? So what this really means is that the interactions between attractive polarons are actually not constant. They're scaling with the electron density. As I reduce the electron density, interactions become larger. And the maximum value we could measure is 35 times the interaction between two excitons. Okay? And the understanding of this is again, one can use this variational ansatz, the Chevy ansatz, but maybe pictorially is better what I tried to explain to Mark. So basically, when I form an attractive polaron, I try to form a trion, and this has a very small size, a bore radius of 2 nanometers. But to grab an electron around the position of the exciton, I have to deplete the Fermi sea. Okay, and this hole in the Fermi sea has a size of the Fermi wavelength. At low density, the size gets bigger and bigger, and therefore, if you, in an ideal world, if I had only 1 electron, then I will have a giant nonlinearity, right? Because I can only form 1 dressing around the exciton. So this is the sort of understanding as to why the interactions are getting dramatically increased. Okay, and this all is telling us about this picture that whenever we have sort of attractive polaron formation due to dressing by the Fermi sea, or it's, in a way, it's a confirmation of this picture. Yes.
Can you go to the previous slide? So with this cartoon, what is that function? That 1 over n to some.
This one?
You understand, or
yeah? So it actually it does scale as 1 over n. Exactly.
Literally
yeah,
1 over n.
Yeah.
So what is it? U times n that goes as 1 over n, or u goes as 1 over n?
U.
Goes
You see that U times n, that n was the exciton density.
Okay, good.
So this is the electron density.
Right.
So it's the electron density. All right. So now we come to the moire. So this is the system. We have 0 degree. We try to go for 0 degree because of the lattice mismatch of 4.1%. Moire occurs naturally, and then it's much more uniform in such a lattice mismatch scenario because small deviations in angle are to first order suppressed. Okay, so if you know, I thought I had some. Okay, so this is the calculation from Yang Zheng. Actually, DFT predicts that this is type 2 alignment. In reality, it's type 1. And so he corrects for that. But the main point is that you form these flat moire bands. And what is special about this material system, and there's only one other sort of material system like this with type 1 alignment, is that the lowest energy moire band in conduction band and the highest energy balance moire band lie in the same way, right? So the role of tungsten is to first order, unless we go to very high electric fields, is just to provide the moire potential. So the physics, both the electrons are occupying the moly bands as well as the optical excitations. Okay, and this is the DFT calculated band structure. So conduction band has this extremely deep sort of moire potential. The peak to depth is about 60 milli-electron volts. Hopping is 1 milli-electron volt according to DFT. Our magnetism studies suggest that this is more like 0.01 in milli-electron volt. So don't really know why there is such a large discrepancy, but then the size of the Van orbitals are about 2 nanometers, and that gives you a U of 220 milli-electron volts and a nearest neighbor interaction of 13. Just to indicate that this is a system where interactions are very strong, and the finite range interactions have to be.
The gap is comparable to the moire, the band gap.
No, band gap is still 1.9
Still huge.
electrons. Yeah. So
it's not a moire band gap, it's the bare band gap.
yes. Yes. All right, so this is then the spectrum of the moire system. So as a function of electron density. So what is new here is that instead of our 1s exciton, we now have 3 excitons, and these are called the moire excitons. And the way to understand them is that we have this tightly bound object, 1s exciton. Now its center of mass motion is subject to a potential because of the difference between the moire potentials in conduction and balance. And therefore, the center of mass motion is quantized and leads to quantized. There's still bands, but it results in these 3 different exciton moire. Okay, so and then as you dope the electrons, there is the attractive form. I'll come to that later. So let me skip that. I will come back to the trion and the attractive form discussion. So this is another device and showing similar features. Again, we will first look at the no electron case, but I also want to show that in addition to the attractive polaron, as we increase the electron density, we see these cusps in reflectivity, and these are the correlated mode states at nucleus 2 and nucleus 2. Okay, so in a related material system, Fan Wang actually has used STM to image these, and it's actually interesting physics in terms of how the electrons are correlated in these states. Okay, so I'm not sure how much we can say about this with nonlinear spectroscopy, but just do that. So we first look at the new charge neutral regime. So we have 2 predominant exciton lines, MX1 and MX2. We tune our pump again to the red side. The probe, as I said, is broad and covers the response of both of the exciton lines. Okay, and you see that the predominant shift together with the free induction decay peaks is from the MX1 because that's the one we're closer to. But you can see that the second line is also shifting to the blue, and this becomes clearer if we differentiate, we take out the no pump case, that these contrasts, red and blue, is telling us about the pollution. Okay. Now, if you look at the, again, the detuning dependence, it is 1 over detuning squared, and it's the case for both of them. And in this case, for example, if really we were only looking at interaction for the excited state between MX2 excitons with each other, then we would have obtained a dependence on detuning of this dotted line, because our detuning is very large and it's not changing as fractionally as much as it does for MX. Okay. So what these fits are telling, I didn't do a very good job in explaining, but what is really happening is that we're generating a coherent population in MX1, and then we're looking at interaction of those coherent excitons, moire excitons, with the ones that we inject to MX1 with the probe beam, or the ones that we inject to MX2. Okay? So the important point here is rather non-qualitative information. It tells us that even though these are sort of orthogonal excitonic modes, they have spatial overlap. They have spatial overlap because interactions are contact-like, and you clearly see that if you generate MX1, MX2 excitons see a shift associated. Okay, so that's kind of, as I said, a qualitative but nice piece of information. If we then look at high doping, so probe the region around nucleus 2 and 3. So in reflection, amplitude, so this is the oscillator strength, you see that there are these peaks at the nucleus 2 and 3. Okay, so the origin we do not exactly know, but we believe that this is due to the fact that whenever you have a gap state, the oscillator strength is not as efficiently transferred to other resonances. So it's really more the bare oscillator strength of the exciton. If you look at the nonlinear response, this is what you see here, is that the nonlinear shift actually has a minimum both at nucleus 2 and nucleus 3. And this is despite the fact that, you know, the oscillator strength is larger, we're generating more excitons, but the interactions are going down. And this, again, very qualitatively, most likely has to do with the fact that the electrons are inactive at this point. They're all gapped, and therefore the interactions are reduced to what they would have been in the absence of electrons, only when the system is polarized. Okay, now maybe the more interesting part, the attractive polaron. So this is the part that I skipped. So what is really interesting here is that if you look at this line and measure its oscillator strength by TM fits, you find that the oscillator strength increases linearly until nucleus 1. This is the same behavior that we saw for the monolayer, but then from nucleus 1 on, it decreases linearly as well towards. And the explanation for this is that, maybe I go back now, is that, you know, once we sort of field every, so the attractive polaron is linked to the trion. So when I have an electron, I can actually generate a trion-like excitation, and it's the hybridization of these trion-like excitations that gives rise to the attractive polaron. But if I have filled all sites with one electron, then I have the maximum possibility to generate the trion. But if I fill all sites with 2 electrons, then there is no way to generate the trion, and therefore the oscillator strength should go to 0. So I'm not sure if I did a good job there, but you can ask me if that is not clear. So this is then the AC Stark shift of the attractive polaron. And what is really remarkable here is that in stark contrast to what we saw for the monolayer, if you look at the moire filling or electron density dependence, this is maybe the misleading scale, but the light shift is essentially constant. It doesn't depend on the electron density. The oscillator strength increases, decreases dramatically, but unlike the monolayer case, that here the shift is essentially changing within 10% of its maximum value. So the understanding here, so I don't have a slide for this, is that this would be the case if we abandon this many-body picture and say that, well, we have all these uncorrelated sites, right? The hopping is very weak. So all I'm doing in this case for attractive pollen is I generate a triome at different sites. But these triomes, because of the small hopping, they do not hybridize. They do not hop from one side to another, which means that if I generate a triome here, it has the other side knows nothing about it. Okay, so then you recover the fact that the interaction is essentially independent of whether you have electrons elsewhere. Actually, this plot I'm missing. We also looked at the detuning dependence, and in this case, it's fit by a big. Okay, so it's basically the main result here is that the nature of these electron dressed excitations can also be very different, and the nonlinear spectroscopy tells us about them, whereas linear spectroscopy is. Okay, and this is our first take on, let's say, what happens if you go resonant and try to basically modify the system by creating kind of a Bose-Fermi mixture, in the sense that we resonantly drive and try to excite sort of, now we want to call this triomes in this moire sites. And if you do cross-circular polarization, nothing happens. And this is something we expect, because the pump generates a triome at a certain number of sites with that is allowed with that polarization. The probe, when it comes, it is not going to see those, and basically there is no blue shift whatsoever. With the cross-linear polarization, this is not the case, because they see each other, and then there is a reduction of the oscillator strength as we excite the system with cross-linear polarization. In this case, the oscillator strength goes down to 50%, because the pump saturates the transition, makes 50% of the sites unavailable, and that results in this reduction. Okay, and so let me conclude. So basically, one way one can extend this into quantum optics direction is that we can value polarize electrons with the magnetic field and use circular polarized excitation to basically invert each site, and in this way realize an inverted decay model, and then study physics like subradiance as versus superradiance. One can argue that if there are interactions with electrons in another layer, like in the heavy fermion model, we can actually use light to turn off these interactions, and in this way do a quench type experiment with the Kondo lattice system. And maybe a bit further down the road is the question of whether we can actually generate interacting Bose-Fermi mixtures. Thank you.
One question about your plot in the beginning when you showed how interaction with interacting polarons was going as 1/n. Somehow it's an interaction which depends on having fermions, and we're used to no energy scale should exceed Fermi energy. So somehow you're going to the regime of lower and lower carrier density, and it would seem like somewhere that rise has to be cut off by the Fermi energy.
No, I would say that in this picture, the cutoff is determined by the trione binding energy, right? Because the amount of nonlinearity. So as I said, let's assume that we have one electron in our optical spot. The first photon comes and generates a trione. In this case, there is no point in calling it even an attractive photon. Now the second photon comes. There is no electron to dress it, so the only resonance it can excite is the bare excitation. So, and the energy difference is the trione binding. So it's not going to be the Fermi energy, but in this case, something much higher at this low density limit, which is the trione binding.
So if U times N is a constant in the zero density limit, is that a number that's? Like, what is that?
Yeah, so basically, so that has been calculated because it plays a central role in polaritons, particularly in gallium arsenide. It's basically is given by E square over epsilon times Bohr radius.
Yeah.
And you can understand it like this, right? So basically, if the interactions are short range, clearly, like the coupling is 1 over r to the 6, and the dominant term comes from when the two guys sit on top of each other, the two excitons can exchange electrons or holes. So you can think of this as a sort of an equivalent potential that says that the two excitons do not see each other, except if they are within a Bohr radius, the interaction strength is the exciton line. And if you do this, you basically within a factor of 6, there's an exchange integral, you get the right order. And it is a constant, unless your density starts to change the binding, the Bohr radius, and so then there will be
Questions? I'm sure you said it. What temperature is this?
sorry, this is all at 4 Kelvin.
All for It's just not particularly sensitive to temperature.
No.